Imagine a world where the vast, serene oceans suddenly rise in a colossal, unexpected upheaval, transforming into towering walls of water that dwarf the tallest structures humanity has ever built. These phenomena, known as mega-tsunamis, are not merely the stuff of disaster films or ancient legends, but are rare, scientifically intriguing events that have shaped our planet's history in profound ways. As we embark on this journey into the depths of geological time and the intricate dance of earth and sea, we invite you to join us in exploring the fascinating science behind these monumental waves. The term mega-tsunami often evokes images of cataclysmic waves sweeping across coastlines with an unstoppable force. But what precisely qualifies as a mega-tsunami? In the essence of scientific precision, a mega-tsunami is characterized by its extraordinary wave height, towering much higher than typical tsunamis generated by underwater seismic activities. While standard tsunamis, born from the shifting of tectonic plates, can reach great distances across oceans, mega-tsunamis are usually the result of a sudden, massive dislocation of water, often triggered by landslides, volcanic collapses, or even the rare asteroid impact. To comprehend the awe-inspiring scale of a mega-tsunami, it's beneficial to compare them with their more common counterparts, seismic tsunamis. These are generated by the vertical displacement of the sea floor during an earthquake, a process that releases a surge of energy, creating waves that travel across vast oceanic expanses. While seismic tsunamis can be devastating, their wave heights are relatively moderate compared to those of mega-tsunamis, which can exceed hundreds of meters as they make landfall. The key difference lies in the mechanism of their formation, which imbues mega-tsunamis with their terrifying potential and rarity. Despite their formidable nature, mega-tsunamis are exceptionally rare, and their occurrence is often confined to specific geographical and geological conditions. This rarity, however, does not diminish their significance. On the contrary, their study offers invaluable insights into the dynamics of Earth processes and the history of our planet's surface. By understanding how and why these monumental waves form, we gain a deeper appreciation of the delicate balance that governs our world's natural systems. In the grand timeline of Earth's history, mega-tsunamis have left indelible marks, shaping coastlines and influencing ecosystems. They remind us of the planet's immense power and the impermanence of our human constructs. While the thought of such events may be unsettling, it is through scientific inquiry and preparedness that we can hope to mitigate their impact and learn from their lessons. As we venture further into this exploration, we will encounter the myriad ways in which mega-tsunamis manifest, from the dramatic landslides of steep volcanic islands to the ancient hidden scars left by prehistoric impacts. Each chapter will unravel a different facet of these extraordinary natural phenomena, providing a tapestry of knowledge woven from geology, oceanography, and history. Before we delve further, we'd be delighted if you could share with us the time and place from which you're listening. And if our exploration piques your curiosity, please do consider subscribing to The Wandering Mind for more insights into our wondrous world. In the vast and enigmatic theater of the Earth's oceans, tsunamis play a role both profound and mysterious, conjuring images of towering walls of water reclaiming the land. To understand the mechanics behind these formidable waves, we must first peer beneath the surface into the complex interplay of geological forces and oceanic dynamics that give birth to them. At their core, tsunamis are a manifestation of energy transfer, a sudden and often violent displacement of water that sets an entire ocean into motion. Unlike the waves we see lapping at our shores on a gentle day, propelled by the wind skimming across the ocean's surface, tsunamis are born from the depths, the result of vertical movements of the sea floor. This vertical displacement is typically triggered by seismic activities, such as earthquakes, but can also stem from volcanic eruptions, landslides, or even the rare impact of celestial bodies. Imagine for a moment the Earth's crust as a giant jigsaw puzzle, its pieces constantly nudging and jostling against one another. At the boundaries of these tectonic plates, stress builds over time until it is released in a sudden, powerful shift. If this shift occurs beneath the ocean, the sea floor may abruptly rise or fall. This vertical movement displaces the overlying water column, creating a series of waves that radiate outward across the ocean, much like ripples spreading from a stone thrown into a pond. The energy of these waves is distributed throughout the entire column of water, from the surface down to the sea floor, distinguishing tsunamis from more common wind-driven waves, which only affect the upper layers of the ocean. This difference in energy distribution is crucial, for it allows tsunamis to travel across entire ocean basins with minimal loss of energy. Indeed, a tsunami can traverse the vast expanse of the Pacific Ocean at speeds comparable to a commercial jetliner, its energy preserved as it races across the deep ocean. As these waves approach shallower coastal waters, their behavior transforms dramatically. In the open ocean, a tsunami may pass unnoticed, just a gentle rise and fall of a few centimeters. However, as the waves encounter the continental shelf, they slow, their energy compressing into a smaller volume of water. The result is a towering wall of water, capable of inundating coastal areas with devastating force. This transformation is dictated by the principles of wave dynamics, rooted in the conservation of energy. As the water depth decreases, the wave's speed diminishes, but its height increases, a process known as wave shoaling. The wavelength shortens, and the energy that was once spread across kilometers of ocean surface is now concentrated in a much smaller area. It is this ability to concentrate energy so efficiently that renders tsunamis so powerful and, at times, so destructive. And yet, despite their fearsome reputation, the science of tsunamis is as much about understanding their nature as it is about appreciating their rarity. For while the Earth's oceans are vast and its tectonic activity frequent, the precise conditions necessary to generate a tsunami of significant magnitude are far less common. In studying tsunamis, scientists rely not only on theoretical models, but also on historical records and modern technology. Seismic networks and ocean buoys provide real-time data, allowing researchers to track the genesis and propagation of tsunamis. This wealth of information aids in refining our understanding of these natural phenomena and in developing early warning systems designed to mitigate their impact on human life. As we delve deeper into the world of tsunamis, it becomes clear that they are not merely waves, but rather a complex natural phenomenon shaped by the intricate dance of geological and oceanographic forces. They remind us of the Earth's dynamic nature, its ability to surprise and challenge us, and the importance of continued observation and study. In this exploration, we begin to see how the forces that create tsunamis are both ancient and ongoing, a testament to the ever-changing face of our planet. From the silent shifting of tectonic plates beneath the ocean floor to the dramatic rise of water as it meets the shore, tsunamis are a vivid illustration of the interconnectedness of Earth's systems. As we ponder the mechanics of these waves, we gain not only a deeper understanding of their nature, but also a greater appreciation for the powerful forces that shape our world. In this reflection, we find ourselves at the intersection of science and wonder, where knowledge deepens our curiosity and inspires us to look anew at the world around us. For in understanding the fundamentals of tsunamis, we not only learn about the mechanisms that drive these waves, but also about the resilience and adaptability of life on Earth. It is a journey of discovery, one that invites us to explore the mysteries of the deep and to marvel at the power and beauty of nature. In the serene majesty of the natural world, where mountains stand stoic and waters flow with an ancient grace, lies an often overlooked phenomenon capable of extraordinary disruption, the landslide-driven tsunami. These formidable waves, born from the sudden displacement of mass, offer a remarkable glimpse into the Earth's dynamic processes. Unlike the more commonly recognized seismic tsunamis, which are catalyzed by undersea earthquakes, landslide-driven counterparts arise from the rapid descent of earth and rock, cascading into water bodies with a force that can be both terrifying and awe-inspiring. The mechanics of these events are rooted in the principles of physics, where the swift transfer of energy from falling debris into water can set off massive waves. Imagine, if you will, a colossal rock as it detaches from a cliff face, plummeting into the sea below. This scenario resembles a stone skipping across the surface of a pond, but on a monumental scale. The water, displaced by the incoming mass, surges upward and outward, creating waves that can travel vast distances. In confined environments such as fjords or narrow bays, the energy is concentrated, often resulting in waves of staggering height and power. Fjords, with their steep, towering walls, are particularly susceptible to such events. These glacially carved valleys, filled with seawater, provide a theater where the drama of landslide-driven tsunamis often plays out in startling detail. The geography of fjords can amplify wave heights as the energy reflects off the steep sides, converging to produce waves that are both tall and swift. Such was the case in Norway's Tafjord in 1934, where a rock slide generated a wave that reached heights of up to 62 meters, claiming lives and altering the landscape. Volcanic islands, too, serve as prime stages for these mega-waves. The geology of these islands, often characterized by unstable slopes and loose volcanic material, can lead to dramatic collapses into the ocean. The Hawaiian Islands, for example, bear geological scars of ancient landslides, reminders of past events where entire flanks of volcanoes have slipped into the sea, sending tsunamis radiating outward. These events, although rare on a human timescale, are part of the natural cycle of island evolution, driven by the relentless forces of gravity and erosion. Beyond the immediate thrill and terror such events might evoke, landslide-driven tsunamis remind us of the Earth's capacity for self-renewal and change. They are a testament to the planet's dynamic nature, where every mountain and valley is subject to the whims of time and the inexorable pull of gravity. The study of these phenomena not only provides insights into past geological events, but also aids in understanding potential future risks. Despite their potential for destruction, landslide-driven tsunamis are scientifically significant, offering a window into the interplay between land and sea. By examining the sediments left behind by these waves, scientists can reconstruct past events and better predict future occurrences. The evidence of ancient waves can often be found in the form of deposits far above normal high tide levels, serving as geological records of the immense forces once unleashed. In the modern age, technology plays a crucial role in monitoring and understanding these events. Satellite imagery, GPS, and sonar mapping allow scientists to identify potential landslide zones and assess their stability. By studying the conditions that lead to past tsunamis, researchers can develop models that predict how similar events might unfold, providing valuable information for risk assessment and disaster preparedness. The narrative of landslide-driven tsunamis is one of both caution and appreciation. It invites us to marvel at the Earth's power while acknowledging our vulnerability in the face of such natural phenomena. As we continue to explore these giants of the deep, we gain not only knowledge but a deeper connection to the planet we call home. Through the lens of landslide-driven tsunamis, we are reminded of the delicate balance that governs the natural world, where each element, from rock to water, plays a role in the grand tapestry of life. In understanding these waves, we come to appreciate the forces that shape our environment, urging us to tread carefully and with respect upon the Earth's surface. As we peer into the depths of time and space, the story of landslide-driven tsunamis serves as a poignant chapter in the ongoing saga of our planet's geological evolution. In the serene expanse of the Alaskan wilderness lies Lituya Bay, a fjord of profound beauty and quietude. Yet, beneath its tranquil surface, the bay harbors a dramatic tale of nature's raw power, a testament to the dynamic forces that shape our planet. On the night of July 9, 1958, Lituya Bay became the stage for an extraordinary event, one that produced the largest wave ever recorded in human history. This was not a story of a distant ocean crossing, but rather an immense surge confined within the bounds of this picturesque inlet. The event was precipitated by a colossal rockfall along the steep cliffs that encircle the bay. Triggered by a magnitude 7.8 earthquake along the Fairweather Fault, a staggering 30 million cubic meters of rock abruptly detached from the mountainside, cascading into the waters of Gilbert Inlet at speeds exceeding 60 kilometers per hour. The sheer kinetic energy of this mass, as it plunged into the bay, displaced an unimaginable volume of water, creating a towering wave that swept across the fjord. The geometry of Lituya Bay played a crucial role in the wave's formation and behavior. Shaped like a T, the bay's long, narrow arms funneled the enormous energy of the wave, directing it upwards and outwards. As the wave surged through the confined space of Gilbert Inlet, it gained height, reaching an astonishing run-up of 524 meters on the opposite slope. This staggering wall of water stripped the trees from the land, leaving a stark line etched into the landscape, a scar that remains visible to this day. Remarkably, Despite its unprecedented size, the wave's impact was largely confined to the bay itself. The enclosed nature of the fjord, combined with the rapid dissipation of energy as the wave traveled, ensured that it did not extend into the open ocean with any significant force. This localization of impact is a defining characteristic of such events, where the interplay between geological features and hydrodynamic forces dictates the wave's reach and intensity. The Lituya Bay event provides a fascinating glimpse into the mechanics of mega-tsunamis and the conditions necessary for their occurrence. The combination of a steep, unstable slope, a significant seismic trigger, and a confined water body created the perfect storm, so to speak, for the generation of this colossal wave. Yet, it also highlights why these events are exceptionally rare. The precise alignment of these factors is uncommon, and even when they do occur, the effects are often limited to the immediate vicinity. In the aftermath of the 1958 event, scientists have meticulously studied Lituya Bay, using it as a natural laboratory to understand the dynamics of such extreme waves. The data gathered has been instrumental in refining models of wave behavior and in developing strategies for assessing tsunami risk in comparable environments. The lessons learned extend beyond the realm of academic interest, providing valuable insights into the potential hazards faced by communities living in similar geological settings. For the few individuals who witnessed the event firsthand, the experience was both terrifying and awe-inspiring. Accounts from survivors described the night sky lit by the eerie glow of the aurora, juxtaposed with the deafening roar of rock and water in motion. Boats anchored in the bay were lifted like toys, carried over the forest and deposited back into the water, a testament to the wave's formidable power. Despite its isolation, the Lituya Bay event has captivated the imagination of scientists and the public alike. It serves as a reminder of the Earth's dynamic nature and the forces that continue to shape its landscapes. While the prospect of encountering such a wave is remote for most, the event underscores the importance of preparedness and respect for the natural world. In considering the implications of the Lituya Bay mega-tsunami, we are prompted to reflect on the broader context of natural disasters. While human ingenuity has allowed us to predict and mitigate many hazards, the forces of nature are often beyond our control. Events like the one in 1958 challenge us to remain vigilant, to study and learn from the past, and to strive for a deeper understanding of the planet we call home. As we delve into the story of Lituya Bay, we are reminded of the delicate balance between stability and change, a balance that is constantly being negotiated by the Earth's geological processes. The scars left by the mega-tsunami are a testament to a singular moment in time, a dramatic expression of the planet's ceaseless transformation. And while such events may be rare, they serve as poignant reminders of the extraordinary forces at play beneath the surface of our everyday lives. In the quiet and remote corners of our planet, where the Arctic winds whisper through vast stretches of untouched wilderness, lie the silent traces of a tumultuous past. The landscapes of Alaska and Greenland, known today for their dramatic ice-covered peaks and rugged coastlines, have witnessed natural forces of immense power, forces that have carved their stories into the very rock and ice. As we delve into this chapter, we invite our minds to wander back in time, to a period when the Earth was sculpted by colossal movements, movements that have left behind clues for us to decipher. The geological evidence for these ancient megawaves, hidden in the layers of sediment and the scars upon the land, offers a fascinating glimpse into the dynamic history of our planet. Alaska, with its towering mountain ranges and expansive fjords, has been shaped by the interplay of tectonic forces, glacial activity, and the inexorable passage of time. It is here, in this rugged terrain, that we find compelling evidence of prehistoric slope failures, events that once triggered giant waves with the power to transform the landscape in a matter of moments. The story of these waves begins with the glaciers themselves, those mighty rivers of ice that have, over millennia, sculpted the valleys and fjords of Alaska. As glaciers advance and retreat, they destabilize the slopes that flank them. The weight of the ice, combined with the erosive power of meltwater, can lead to massive landslides. When these land masses plunge into the fjords, they displace vast volumes of water, generating waves that surge through the narrow channels with devastating force. One notable example of such an event is found in Taian Fjord, where in 2015 a landslide occurred following the retreat of the Tyndall Glacier. This event, though recent, offers a window into the types of geological processes that have likely occurred repeatedly over the millennia. The landslide displaced over 120 million tons of rock and debris, creating waves that reached heights of up to 193 meters. Although the 2015 event is well documented, similar occurrences have undoubtedly taken place in the distant past, their evidence now concealed beneath layers of sediment. As we shift our gaze across the icy waters to the vast expanse of Greenland, we uncover a similar narrative. Here, the interplay between ice and land is even more pronounced. Greenland's massive ice sheet, one of the largest on Earth, holds within it the potential for significant geological activity. When the ice sheet undergoes periods of rapid melting or calving, it can lead to the destabilization of adjacent slopes, triggering landslides that generate waves capable of traveling great distances. The evidence for past giant waves in Greenland is found in the form of marine deposits far inland, where the sea should never have reached. These deposits, rich in microfossils and marine sediments, tell a tale of enormous waves that once swept across the land, carrying with them the remnants of the ocean. Such deposits, when carefully dated using techniques like radiocarbon dating or optically stimulated luminescence, provide a timeline of these cataclysmic events. But what, we might wonder, is the broader significance of understanding these prehistoric megawaves. Beyond the awe they inspire, they serve as reminders of the forces at work beneath the serene surface of our planet. In a world increasingly concerned with the impacts of climate change, these ancient events highlight the interconnectedness of Earth's systems. As global temperatures rise and ice continues to melt, the potential for similar occurrences may be heightened, prompting scientists to study these past events with renewed vigor. It is through the lens of these geological records that we gain insight into the past behaviors of our planet's most extreme natural phenomena. By piecing together the evidence of prehistoric megawaves in regions like Alaska and Greenland, we build a more comprehensive understanding of the mechanisms that drive such events. The shifting of the Earth's crust, the relentless advance and retreat of glaciers, and the immense forces of gravity and momentum all play a part in shaping these dramatic episodes of natural history. And while the likelihood of experiencing such events in the near future remains low, the lessons gleaned from these ancient waves serve to inform our understanding of the Earth's dynamic processes, reminding us of the ever-present power of nature. As we continue our exploration, let us carry with us the knowledge that the story of our planet is written not only in the stars above, but also in the rocks beneath our feet, in the silent echoes of waves that once roared with unimaginable force. Through this understanding, we find a deeper appreciation for the delicate balance that sustains life on Earth, a balance that has withstood the test of time and will continue to do so long into the future. In the deep past, long before the whir of modern civilization, the Earth was already a dynamic, restless entity. One of the most intriguing episodes in its recent geological history is the Storegga Slide. This was an event so vast and powerful that it shaped the seascape and affected human history in ways we are only beginning to comprehend. The Storegga Slide took place approximately 8,150 years ago beneath the cold waters of the Norwegian Sea. It was a colossal underwater landslide, one of the largest known to have occurred anywhere on Earth. The name Storegga itself translates to the Great Edge, aptly describing the steep continental slope where it all began. To visualize the scale, imagine an area of seabed roughly the size of Iceland suddenly collapsing, sending an unimaginable volume of sediment tumbling into the abyssal depths. The total volume of displaced material is estimated to have been around 3,500 cubic kilometers, a staggering amount by any measure. Geologists believe that the cause of this monumental slide is linked to a combination of factors. One of the primary suspects is the destabilization of sediment layers due to the melting of ice sheets. As the last glacial period drew to a close, vast quantities of ice that had accumulated over millennia began to melt. This melting not only increased sea levels, but also released immense pressure from the land. The continental shelves, once heavily laden with ice, began to rebound, a process known as isostatic adjustment. This created a delicate balance where the sediments, waterlogged and weakened, became susceptible to collapse. Additionally, the presence of gas hydrates along the continental shelf may have played a crucial role. These are ice-like structures that trap methane within their crystal lattice. As the ocean warmed and pressure conditions shifted, these hydrates could have destabilized, releasing methane gas and further weakening the sediment layers. This combination of factors, rebounding land, melting ice, and gas hydrate destabilization, created a perfect storm, setting the stage for the Storegga Slide. The immediate consequence of this event was a massive tsunami that swept across the North Atlantic. Evidence of its reach is found in geological deposits as far afield as Scotland, the Faroe Islands, and even the eastern coast of Greenland. Waves estimated to have been up to 20 meters high crashed against the coastlines, inundating vast areas. In the low-lying regions of what is now Scotland, these waves left behind layers of sand and marine debris, silent witnesses to the fury of the sea. The effect of the Storegga Slide on human populations of the time is a subject of ongoing research and speculation. During this period, Mesolithic communities were gradually transitioning to more settled ways of life, with small groups living along the coastlines of Europe. The sudden arrival of such a tsunami would have been catastrophic, potentially wiping out entire communities and forcing survivors to move inland. Some archaeologists hypothesize that this event may have accelerated cultural shifts and migrations, influencing the development of prehistoric societies. What makes the Storegga Slide particularly fascinating is not just its scale, but also its implications for understanding the dynamics of our planet. It serves as a reminder of the potent forces lurking beneath the ocean's surface, forces capable of reshaping our world in an instant. Furthermore, it highlights the interconnectedness of Earth's systems, how the retreat of ice, the shifting of land, and the release of subterranean gases can combine to trigger events of staggering magnitude. In contemplating the Storegga Slide, we are also compelled to consider the possibility of similar events occurring in the future. The geological processes that led to this ancient landslide are still very much at play today. As climate change continues to influence ice melt and sea temperatures, the potential for future slides and their accompanying tsunamis is a subject of scientific inquiry and concern. Modern technology allows us to map the ocean floor with unprecedented detail, revealing the scars of past events and the potential triggers of future ones. By studying the Storegga Slide, scientists hope to refine predictive models and improve early warning systems to mitigate the impact of any future occurrences. It is a delicate balance, understanding the ancient past to safeguard the future, and the Storegga Slide is a crucial piece of that puzzle. As we reflect on this ancient event, we are reminded of the fragility of human existence in the face of nature's grandeur. The Storegga Slide serves as both a cautionary tale and a testament to the resilience of life. How, despite the cataclysmic forces that shape our planet, life endures, adapts, and thrives. In the quiet contemplation of these ancient underwater forces, we find a narrative that is as humbling as it is enlightening. The story of Earth is one of restless change. Beneath our feet, continents drift imperceptibly on their tectonic plates, sculpting the landscape over eons. Yet, there are moments when this change is anything but gradual, times when nature's forces unleash their pent-up energy in a sudden, dramatic display. Among these are the colossal waves known as Mega-Tsunamis, often triggered by the collapse of volcanic island flanks. These titanic waves, though rare, remind us of the power and unpredictability of our planet's geology. Volcanic islands are born from the fiery crucibles deep within the Earth. As magma rises and erupts onto the ocean floor, it cools and solidifies, gradually building underwater mountains that eventually breach the surface to form islands. Over time, these islands grow as successive eruptions layer new rock atop the old. However, this process also lays the groundwork for potential instability. Unlike more ancient continental landforms, volcanic islands are relatively young and structurally precarious, their sides steep and their foundations often riddled with weaknesses. The Hawaiian Islands provide a telling example. These islands are part of a volcanic hotspot, a stationary plume of molten rock rising from deep within the Earth. As the Pacific Plate moves over this hotspot, a chain of volcanoes is formed. While we often marvel at the beauty of Hawaii's lush landscapes and fiery eruptions, beneath this exterior lies a more ominous potential. The very forces that create these islands also set the stage for their dramatic transformation. The steep slopes of volcanic islands, combined with their rapid growth, can lead to gravitational instability. As the islands accumulate mass above sea level, the enormous weight can stress the underlying rock. Over time, fractures may develop, especially where layers of volcanic rock are interspersed with weaker materials such as ash or clay. Rainwater seeping into these fractures can further weaken the structural integrity of the island. Add to this the constant pounding of ocean waves at the base of these islands, and the stage is set for a potential collapse. When a section of a volcanic island fails, it does so with staggering speed and force. Imagine a vast slice of mountainside suddenly breaking away and plunging into the ocean. This rapid displacement of rock generates an immense wave, a mega-tsunami that radiates outwards with devastating potential. The speed and size of the wave depend on various factors, including the volume of rock that collapses and the geometry of the island and surrounding seabed. The Canary Islands offer another example of this phenomenon. These islands, located off the northwest coast of Africa, are the tips of ancient volcanoes. Geological studies suggest that several of these islands have experienced significant landslides in the past. La Palma, one of the islands, has been of particular interest to scientists. Its western flank, known as Cumbre Vieja, is considered at risk of collapse. Models have suggested that if this flank were to fail, it could generate a tsunami capable of crossing the Atlantic, impacting coastlines as far away as the eastern United States. However, it is important to balance these scenarios with scientific caution. While the potential for a catastrophic collapse exists, the probability of such an event occurring in the near future is low. Modern research has shown that these processes are complex and influenced by a multitude of factors. Advances in geological monitoring and modeling have allowed scientists to reassess earlier, more alarming predictions. Observations suggest that rather than a single, massive collapse, a more likely scenario involves smaller, staged failures over time, which would significantly reduce the tsunami's potential impact. The study of volcanic island collapses is not just about understanding past events, but also about preparing for future possibilities. By using satellite imagery, seismic monitoring, and ground-based surveys, scientists strive to detect early signs of instability. Such efforts are crucial in providing early warnings and mitigating potential risks to coastal communities. In reflecting upon these mighty forces, we are reminded of the delicate balance that exists between creation and destruction. Volcanic islands are a testament to the dynamic processes that shape our world, offering both beauty and danger in equal measure. As we continue to explore and understand these natural phenomena, we gain not only knowledge, but also a profound appreciation for the intricacies of our planet. In the end, the story of volcanic island collapses and the mega-tsunamis they can generate is a lesson in respect for nature's power. While we may never fully predict or prevent such events, through careful study and preparedness, we can hope to coexist more harmoniously with the forces that have shaped and will continue to shape our world. As we delve into the intricacies of the Cumbre Vieja scenario, we find ourselves on the island of La Palma, part of Spain's Canary Islands. This volcanic island, with its rugged landscapes and vibrant culture, conceals beneath its surface the potential for dramatic geological activity. It is here that early models once painted a picture of impending doom, a catastrophic collapse capable of sending a tsunami racing across the Atlantic. However, modern research invites us to reassess such scenarios with a more nuanced perspective. In the late 1990s, a series of studies suggested that the western flank of Cumbre Vieja was primed for a massive landslide. These studies postulated that such an event could displace a vast volume of water, unleashing a tsunami that might reach the eastern seaboard of the Americas, with significant effects even in Europe and Africa. The idea of such a cataclysmic wave captured the imagination of the public and media alike, fueling both curiosity and concern. Yet, as is often the case in science, early hypotheses demand rigorous scrutiny. Over the years, geologists have returned to La Palma with improved methods and technologies, seeking to understand the true nature of the island's volcanic dynamics. Through seismic surveys, satellite observations, and field studies, a more detailed picture has begun to emerge. The initial models suggested that a single massive collapse could occur in one swift movement. However, more recent investigations propose a less dramatic, more fragmented scenario. It appears increasingly likely that any potential future landslide would occur in stages rather than an instantaneous slide into the ocean. This staged collapse would result in considerably smaller waves, with much less energy to traverse the vast distances of the Atlantic. This updated understanding stems from a deeper appreciation of the island's geological structure. The internal architecture of Cumbre Vieja is complex, with layers of ancient lava flows, volcanic ash, and pyroclastic material interspersed with weaker sediments. This intricate layering acts to compartmentalize potential failure zones, making a single colossal slide less feasible. Furthermore, the forces required to initiate such a collapse are vast. While volcanic activity and earthquakes are common in the region, the specific conditions necessary to trigger a complete flank failure are rare. This is not to say that the risk is non-existent, but rather that the apocalyptic scenarios of yore should be relegated to the realm of low-probability events. The Atlantic's potential tsunami risk, therefore, becomes a question of scale and likelihood. Smaller landslides could indeed produce localized waves, affecting nearby coasts. However, these would lack the energy to maintain destructive power across the ocean. The scientific community remains vigilant, recognizing that while the risk is reduced, it is not entirely absent. As we reflect on the implications of these findings, it is important to consider the broader context of human habitation and preparedness. Coastal communities in the Canary Islands, the Azores, and beyond are all too familiar with the restless nature of their environment. Vigilance and preparedness remain key, guided by the insights provided by ongoing research. Technological advances have greatly enhanced our ability to monitor and model these natural processes. Continuous GPS monitoring, high-resolution satellite imagery, and real-time seismic data contribute to a robust network of observation. This allows scientists to detect subtle changes in the landscape that might precede a significant event. Moreover, the development of numerical models has allowed researchers to simulate various scenarios, assessing potential impacts and refining early warning systems. These models, while inherently limited by the complexity of nature, provide valuable insights that inform both scientific understanding and public policy. The story of Cumbre Vieja is not merely one of potential disaster. It is, fundamentally, a testament to the power of scientific inquiry, and the human capacity to learn from our environment. In revisiting early models and refining our understanding, we reinforce the importance of humility in the face of nature's complexities. This chapter of our exploration serves to remind us that while the forces of the Earth are formidable, they are not beyond our comprehension. Through careful study and international collaboration, we can mitigate risks and foster resilience. As we continue our journey through the world of mega-tsunamis, we carry with us the knowledge that science is ever evolving, ever questioning, and ever committed to the pursuit of truth. In contemplating the Cumbre Vieja scenario, we find both caution and reassurance, a balance that reflects the essence of scientific endeavor. It is a reminder that while certain possibilities remain in the realm of speculation, our understanding is always improving, and with it, our ability to coexist with the dynamic planet we call home. Hawaii, often conjuring images of tranquil beaches and lush landscapes, holds secrets beneath its waves, hidden in the geological scars etched into its ocean floor. These secrets tell tales of immense power and cataclysmic events that dwarf the imagination. Here, beneath the azure waters, lie the remnants of ancient landslides, some of the largest known island collapses on Earth. These colossal events, while not part of the island's daily rhythm today, remind us of the dynamic and ever-changing nature of our planet. To understand these prehistoric landslides, we need to delve deep into Hawaii's geological past. The Hawaiian Islands are volcanic in origin, formed by a hotspot beneath the Pacific Plate. Over millions of years, magma surfaced, creating a chain of islands as the plate moved slowly northwestward. While the serene islands above ground paint a picture of stability, the geological activity below has been far from calm. The key players in these ancient collapses are the towering volcanoes that define Hawaii's landscape. Volcanic islands, by their very nature, are structurally unstable. Over time, as these islands grow, their volcanic edifices become heavy and steep, sometimes leading to colossal structural failures. Imagine the sheer weight of an island like Hawaii, with its volcanic peaks rising thousands of meters above the ocean floor and extending even further beneath the surface. This enormous mass, coupled with steep slopes, creates conditions ripe for monumental landslides. Geologists have identified evidence of these massive landslides through underwater surveys and sediment analysis. Vast fields of debris, known as debris avalanches, are scattered around the Hawaiian Islands, some stretching hundreds of kilometers across the ocean floor. These are not mere piles of rubble. They are the remnants of entire sections of islands that once succumbed to gravity's relentless pull. One particularly notable site lies off the coast of the Big Island, where the Helena slump presents a stark reminder of potential instability. This vast area of fractured rock and sediment suggests past movements and raises questions about future activity. While the exact timing of these ancient landslides remains a subject of ongoing research, clues gleaned from the ocean floor paint a picture of dramatic events occurring over the last few million years. The implications of these ancient collapses extend beyond mere geological curiosity. Understanding these events helps in assessing the current stability of Hawaii's volcanic structures. Each landslide in Hawaii's past speaks to the potential for future activity. While modern technology allows us to monitor these geological features with increasing precision, the sheer scale of past events serves as a humbling reminder of nature's power. Today, scientists employ a variety of sophisticated tools to keep a vigilant watch over Hawaii's volcanic landscape. Satellite imagery, GPS, and seismic sensors are deployed to detect minute movements and shifts within the island's structure. Through these technologies, we gain insight into the behavior of the volcanic giants that slumber beneath the surface, offering some measure of foresight into potential changes. The study of Hawaii's ancient landslides also holds broader implications for understanding volcanic island stability worldwide. Similar processes could threaten other volcanic regions, and the lessons learned in Hawaii provide valuable knowledge applicable to these areas. By examining the past, scientists can better predict future scenarios, aiding in the development of strategies to mitigate potential risks. Despite the ominous nature of these ancient events, it's important to maintain a balanced perspective. While the possibility of another massive landslide is not insignificant, such events occur on geological timescales spanning thousands to millions of years. The likelihood of an immediate threat remains low, but continuous monitoring and research are essential to ensure preparedness. The story of Hawaii's ancient landslides is a testament to the planet's dynamic nature. It underscores the importance of scientific inquiry and vigilance in understanding the forces that shape our world. As we explore these subterranean mysteries, we are reminded of the delicate balance between the Earth's forces and the vibrant life that thrives upon its surface. Hawaii, with its rich history of geological activity, stands as both a paradise and a poignant symbol of nature's raw power. In the end, these ancient landslides invite us to reflect on our place within the grand narrative of Earth's history. They remind us of the interconnectedness of land and sea, of past and present, and of the ongoing dance between creation and collapse that defines our planet. As we continue to study and learn from these geological phenomena, we gain not only knowledge, but also a deeper appreciation for the intricate tapestry of life and landscape that makes our world so remarkable. In the dim light of the early morning hours on the 27th of August, 1883, the world experienced one of nature's most profound displays of power. The island of Krakatoa, nestled in the Sunda Strait between Java and Sumatra, erupted with a force and fury that would echo through history. This cataclysmic event not only altered the geographical landscape, but also provided a chilling insight into the might of submarine volcanic tsunamis. Krakatoa's eruption was not merely a geological event, it was a symphony of natural forces, each note played out in a sequence of explosive crescendos that culminated in a series of devastating tsunamis. These waves were not the product of a simple landslide or the shifting of tectonic plates, but rather the result of a volcanic explosion so powerful that it reshaped the boundaries of the island itself. Such eruptions, while rare, remind us of the intricate interplay between the Earth's crust and the vast oceans that cover most of our planet. The eruption of Krakatoa was marked by a sequence of explosive events, each one more powerful than the last. As magma met seawater, the rapid vaporization of water created superheated steam, resulting in phreatomagmatic explosions. These explosive interactions are pivotal in understanding how volcanic eruptions can generate tsunamis. Unlike the long, rolling waves generated by earthquake-induced tsunamis, those born from volcanic activity are often characterized by their sudden, violent onset and localized impact. When Krakatoa erupted, the sheer volume of volcanic material expelled into the atmosphere was staggering. Ash and pumice covered the skies, while pyroclastic flows cascaded down the slopes of the volcano, meeting the ocean with a ferocity that displaced vast amounts of water. It was this sudden displacement that generated the tsunamis which wreaked havoc on the surrounding coastlines. Traveling at speeds up to 600 kilometers per hour, these waves reached heights of over 30 meters in some places, obliterating everything in their path. The devastation was profound. Coastal towns and villages across the Sunda Strait were engulfed by the waves. It is estimated that over 36,000 lives were lost, making it one of the deadliest volcanic events in recorded history. Yet, despite the tragedy, Krakatoa's eruption offered scientists a unique opportunity to study the mechanisms behind submarine volcanic tsunamis. The lessons learned have been invaluable in understanding how similar events might unfold in the future. Volcanic tsunamis differ from their seismic counterparts, not only in genesis but also in their potential impact. The rapid expulsion of volcanic material can result in a variety of tsunami-generating mechanisms. In addition to the direct displacement of water by volcanic debris, the collapse of volcanic edifices into the sea can also initiate waves. Furthermore, the explosive force of an eruption can create shock waves that propagate through the water, adding another layer of complexity to these events. Krakatoa's eruption also highlighted the global reach of such natural phenomena. The sound of the explosion was reportedly heard as far away as Australia and the island of Rodrigues near Mauritius, over 4,800 kilometers away. Atmospheric pressure waves from the eruption circled the globe several times, demonstrating the far-reaching impact of large-scale volcanic events. This global resonance serves as a reminder of our interconnectedness with the planet's dynamic systems. In the aftermath of Krakatoa, the island itself was forever changed. The volcanic activity had obliterated much of the original island, leaving behind a caldera that would later give rise to a new volcanic island, Anak Krakatau, or Child of Krakatoa. This new formation serves as a living laboratory, allowing scientists to observe and study ongoing volcanic processes. Anak Krakatau remains active, a poignant reminder of its storied past and the potential for future eruptions and associated tsunamis. The legacy of Krakatoa extends beyond the physical and into the cultural realm. The eruption inspired numerous works of literature and art, embedding itself into the collective memory of humanity. It stands as a testament to the awe-inspiring and at times terrifying power of nature. Ultimately, the story of Krakatoa and its tsunamis underscores the importance of understanding volcanic processes. While we cannot prevent such natural events, we can strive to better predict and prepare for them. Advances in monitoring technology and early warning systems are crucial in mitigating the risks associated with volcanic tsunamis. By studying the past, we arm ourselves with knowledge, giving us the best chance to protect lives and infrastructure when faced with the inevitable caprices of our planet. In contemplating Krakatoa, we are reminded of the delicate balance that exists between the Earth's geological forces and the vast expanses of ocean that cradle our continents. This balance, though often serene, holds within it the potential for dramatic upheaval, a narrative written in the language of eruptions and waves, of destruction and rebirth. It is a story that continues to unfold, inviting us to listen, learn, and prepare for whatever the future may hold. In the vast expanse of the Pacific Ocean lies an archipelago that, for much of human history, remained relatively quiet. The Hunga Tonga, Apai Islands, part of the Kingdom of Tonga, served as silent sentinels, their volcanic origins hinting at the forces simmering beneath. Yet, in early 2022, these islands became the scene of one of the most extraordinary natural events in recent memory, a volcanic eruption that sent ripples across the globe, both literally and figuratively. The eruption of the Hunga Tonga, Hunga Ha apai volcano was not just another chapter in the Earth's geological narrative. It was a modern case study in the complex interplay of volcanic activity and its far-reaching impacts. On 15 January 2022, the volcano erupted with a force so immense that it generated pressure waves traveling through the atmosphere at speeds exceeding 1,000 kilometers per hour. These atmospheric shock waves were detected as far as the United Kingdom, a testament to the sheer power unleashed by this underwater colossus. But what made this event particularly intriguing to scientists and observers alike was not just the spectacle of the explosion itself, but the unique combination of phenomena it triggered. The eruption sent a towering plume of ash and gas into the atmosphere, reaching altitudes of up to 58 kilometers, piercing through the stratosphere and into the mesosphere. This was the highest volcanic plume ever recorded by satellite imagery, marking a significant milestone in our observation of such events. The water displacement caused by the eruption was equally spectacular. As the volcano erupted, it displaced massive volumes of water, generating tsunamis that propagated across the Pacific Ocean. However, these waves were different from the typical tsunami waves generated by tectonic activity. The eruption's explosive force created a rapid displacement, causing waves that were initially localized but powerful enough to be felt across vast distances. In parts of Tonga, these waves reached heights of up to 15 meters, causing significant devastation to coastal communities. The eruption also had profound atmospheric implications. The injection of vast quantities of water vapor into the stratosphere has the potential to temporarily alter the Earth's climate. Water vapor acts as a greenhouse gas, and its presence in the stratosphere can lead to increased surface temperatures. While the long-term climatic effects of this particular eruption remain a subject of ongoing study, it serves as a reminder of the interconnectedness of Earth's systems, where an event in one part of the planet can have cascading effects elsewhere. From a scientific perspective, the Hunga Tonga Ha apai event offered a rare opportunity to study underwater volcanic eruptions in unprecedented detail. The eruption was monitored by a suite of modern technology, including satellites, undersea cables, and remote sensing equipment. This wealth of data has provided insights into the dynamics of such eruptions, particularly the role of volcanic gases in generating pressure waves and the mechanisms by which water displacement occurs. The eruption's impact on the local environment was immediate and profound. The islands themselves were significantly altered, with large portions submerged or reformed by the explosive activity. Ashfall blanketed the surrounding areas, affecting air quality and agriculture. The local population faced the dual challenges of immediate physical danger and the longer-term consequences of environmental disruption. Globally, the eruption served as a wake-up call regarding the potential risks posed by submarine volcanoes. While not as frequent as their terrestrial counterparts, underwater eruptions can have wide-ranging impacts due to their ability to generate tsunamis and affect atmospheric conditions. The Hunga Tonga apai event underscored the importance of continuous monitoring and research to better understand these phenomena and their potential to influence both local and global systems. In reflecting on the 2022 eruption, one is reminded of the delicate balance that characterizes our planet. The dynamic processes that shape the Earth's surface and atmosphere are both wondrous and unpredictable. As we deepen our understanding of these forces, we gain not only knowledge, but also perspective, a sense of humility in the face of nature's power, and an appreciation for the intricate web of life that thrives on this ever-changing planet. This event, while remarkable in its own right, also serves as a poignant reminder of the broader narrative of Earth's geological history, a history marked by change and adaptation, where each event, no matter how singular, contributes to the ongoing story of our planet. As we continue to study the Hunga Tonga, Hunga Ha eruption, we are reminded of the importance of scientific inquiry and the role it plays in helping us navigate the complexities of the natural world. In the expansive theater of Earth's history, few events have been as dramatic or transformative as the impact of an asteroid. These celestial wanderers, careening through space, occasionally intersect with our planet in a cataclysmic dance of gravity and momentum. While their visits are rare, the consequences can be profound, leaving an indelible mark on the geological and biological record. Imagine, if you will, a vast, tranquil ocean under a serene sky. Suddenly, the tranquility is shattered as a massive asteroid punctures the atmosphere, blazing a fiery trail across the heavens. Its descent is swift and unstoppable, culminating in an explosive collision with the ocean's surface. In an instant, an immense volume of water is displaced, sending ripples of energy racing across the sea in all directions. This is not merely a ripple effect, but the genesis of a mega-tsunami, a wave of such magnitude that it defies ordinary comprehension. The mechanics of such an event are both fascinating and complex. When an asteroid impacts the ocean, it transfers a colossal amount of kinetic energy to the water, creating a cavity at the point of impact. This cavity rapidly collapses, generating waves that radiate outward. The size and energy of these waves depend on several factors, including the size of the asteroid, its velocity, and the angle of impact. Larger asteroids, striking at high speeds, can produce waves hundreds of meters high, capable of traveling vast distances across ocean basins. One of the most famous examples of an asteroid-induced mega-tsunami is the Chicxulub impact, which occurred approximately 66 million years ago. This event is etched into the annals of Earth's history as a pivotal moment, marking the end of the Cretaceous period and the extinction of the non-avian dinosaurs. The asteroid, estimated to be around 10 kilometers in diameter, struck the Yucatan Peninsula in what is now Mexico. The impact released energy equivalent to billions of atomic bombs, creating a crater over 180 kilometers wide. The Chicxulub impact did more than just create a crater. It unleashed a series of catastrophic environmental changes. The immediate aftermath would have been apocalyptic, with mega-tsunamis racing across the Gulf of Mexico and beyond. Geological evidence suggests that the waves generated by this impact may have reached heights of several hundred meters, inundating coastlines and reshaping the geography of the region. The implications of such a wave are staggering. Coastal areas, home to diverse ecosystems and early life forms, would have been scoured clean by the sheer force of the water. Marine life, already subjected to the shockwaves of the impact, would have faced additional pressures from the churning, turbulent waters. Inland, the effects would have been felt as well, as the atmosphere filled with debris and aerosols, blocking sunlight and leading to a dramatic cooling of the planet, a phenomenon known as an impact winter. Despite the rarity of these events, they remind us of the dynamic and ever-changing nature of our planet. While the probability of a similar asteroid impact occurring in our lifetime is exceedingly low, the possibility, however remote, underscores the importance of continued vigilance and research. Modern astronomy and planetary science have made significant strides in identifying and tracking near-Earth objects. International efforts are underway to catalog asteroids and comets that could pose a potential threat, employing sophisticated telescopes and satellite technology to monitor the skies. This global endeavor not only enhances our understanding of these celestial bodies, but also provides critical data to inform potential mitigation strategies. In reflecting on the power of asteroid-ocean impacts, we are reminded of the interconnectedness of Earth's systems. The forces that shape our planet are vast and varied, from the tectonic movements beneath our feet to the celestial influences from above. Each of these forces plays a role in the grand narrative of Earth's history, influencing the evolution of life and the environment in ways both subtle and profound. As we gaze up at the night sky, it is humbling to consider the vastness of space and the myriad of objects it contains. Each star, each planet, and each asteroid is a testament to the complexity and wonder of the universe. While the threat of an asteroid impact is a reminder of our planet's vulnerability, it is also an invitation to explore and understand the cosmos, to seek out the mysteries that lie beyond our world, and to appreciate the delicate balance that sustains life on Earth. In the end, the story of asteroid-ocean impacts is one of resilience and adaptation. Life on Earth has weathered countless challenges over the millennia, from volcanic eruptions to ice ages, and yes, even asteroid impacts. Through it all, the planet has endured, evolving and transforming in response to the ever-changing conditions. It is a testament to the tenacity of life and the remarkable capacity of Earth to regenerate and renew. As we continue to study and learn from these extraordinary events, we gain not only insights into the past, but also a deeper appreciation for the fragile beauty of our home in the universe. The ocean floors, vast and enigmatic, stretch across our planet like the hidden underbelly of a colossal aquatic beast. Often out of sight and out of mind, these submerged landscapes hold secrets that, while largely silent, have the potential to disrupt life as we know it. One of the most significant threats lurking beneath these waters is the instability of submarine slopes along continental margins. It is here, in the interplay of geology and oceanography, that we find the potential seeds for some of nature's most powerful and sudden events, submarine landslides. Continental margins are the submerged edges of continents, where the land gently slopes down into the ocean depths. They are dynamic environments shaped over millions of years by sedimentation, tectonic activity, and ocean currents. While they might appear stable to the untrained eye, these regions are actually quite complex, prone to occasional instability under specific conditions. One of the primary factors contributing to this instability is sediment loading. Vast quantities of sediment are constantly being deposited on these slopes, carried by rivers, glaciers, and ocean currents. Over time, these sediments accumulate in layers, creating a delicate balancing act between the weight of the sediment and the underlying geological structures. Occasionally, when the balance tips, the result is a catastrophic movement of material, known as a submarine landslide. These landslides can be triggered by a variety of factors. Earthquakes, even those that occur far from the coast, can send tremors through these sediment-laden slopes, unsettling the layers and causing them to shift. The sudden displacement of these massive volumes of sediment can generate significant tsunamis, as the energy from the landslide is transferred to the overlying water. The energy propagates through the ocean, sometimes reaching distant shores with devastating consequences. Another, less obvious but equally fascinating contributor to slope instability is the presence of gas hydrates. These are crystalline structures composed of water and gas, typically methane, which form under the high-pressure, low-temperature conditions found on the ocean floor. Gas hydrates are stable under these conditions, seemingly innocuous as they bind the sediment particles together. However, changes in temperature or pressure, often due to natural shifts or anthropogenic influences, can destabilize these hydrates. When gas hydrates dissociate, the gas is released into the surrounding sediments, reducing their stability. The layers of sediment can become saturated with gas, transforming them into a slurry-like consistency that is susceptible to movement. Should this occur on a slope, it can lead to a rapid and large-scale landslide, with the potential to create a tsunami. Historical records and geological evidence indicate that such events have occurred in the past. The Storegga Slide off the coast of Norway, one of the largest known submarine landslides, serves as a stark reminder of the power of these undersea movements. Approximately 8,000 years ago, an enormous volume of sediment, estimated to be around 3,000 cubic kilometers, was displaced in a series of slides, triggering a tsunami that affected the coastlines of northern Europe. Modern technology has allowed us to map the ocean floor with increasing precision, revealing the scars of past landslides and providing clues about potential future risks. Techniques such as seismic reflection profiling and sub-bottom profiling are employed to examine the layers of sediment and rock beneath the ocean floor. These tools help scientists identify areas of potential instability, where the layers of sediment are thickest or where gas hydrates are abundant. One of the challenges in assessing the risk of submarine slope instability is the sheer scale and inaccessibility of these environments. The ocean is vast, and the detailed study of underwater slopes requires specialized equipment and expertise. Furthermore, The interactions between the various factors contributing to slope instability, sediment loading, gas hydrates, and seismic activity are complex and not yet fully understood. Advancements in our ability to monitor these underwater landscapes have improved significantly in recent years. Remote sensing technologies, combined with in-situ measurements from research vessels and submersibles, provide valuable data that enhance our understanding of these processes. However, predicting when and where a submarine landslide might occur remains a formidable challenge. The implications of submarine slope instability extend beyond the immediate threat of tsunamis. The release of methane from dissociating gas hydrates has potential implications for climate change, as methane is a potent greenhouse gas. The interaction between oceanic and atmospheric systems is intricate, and changes in one can have cascading effects on the other. As our climate continues to change, the stability of these submarine slopes may be further compromised. Rising ocean temperatures, linked to global warming, could lead to the dissociation of gas hydrates on a more widespread scale. Additionally, changes in sea level and ocean currents might alter sediment deposition patterns, further influencing slope stability. Understanding and mitigating the risks associated with submarine slope instability require a multidisciplinary approach. Collaboration between oceanographers, geologists, climatologists, and engineers is essential to develop effective monitoring systems and early warning mechanisms. While the prospect of predicting such events with certainty remains elusive, ongoing research is crucial in enhancing our preparedness and response strategies. In our quest to comprehend the hidden risks on continental margins, we are reminded of the intricate balance that governs our planet's natural systems. Beneath the waves, in the silent world of the ocean floor, lies a reminder of the power and unpredictability of nature. By continuing to explore and understand these environments, we not only uncover the secrets of the past, but also prepare for the challenges of the future. In the serene and remote corners of the world, where land and sea meet with a dramatic embrace, lie the fjords. These majestic, steep-walled inlets carved by glaciers over millennia are not just a testament to the Earth's geological artistry, but also potential theaters for spectacular natural events. Fjords, with their narrow confines and towering walls, have a unique propensity to amplify waves, turning what might be an otherwise moderate disturbance into a formidable phenomenon. The mechanics behind this amplification are rather straightforward yet fascinating. Picture a fjord as a natural funnel. The energy of a wave entering this funnel is constricted and channeled, causing it to rise as it moves through the narrowing passage. Much like how water accelerates through a narrowing hose, the wave gains height, sometimes dramatically. This is why fjords, despite their relatively limited geographical extent, can witness some of the most intense wave activity on Earth. One particularly illustrative example comes from Tern Fjord in Alaska. In 2015, this remote location became the backdrop for an extraordinary natural spectacle. A massive landslide, triggered by the rapid retreat of a glacier, plunged into the fjord, displacing an enormous volume of water. The resulting wave reached astonishing heights, a reminder of the raw power locked within these seemingly tranquil landscapes. The dynamics at play in Tern Fjord were complex. The landslide itself was a consequence of glacial retreat, a process accelerated by our warming climate. As glaciers melt and recede, they destabilize the slopes they once supported. In the case of Tarn Fjord, the retreat of the Tyndall Glacier had been ongoing for decades. With the glacier no longer buttressing the slopes, a colossal section of rock eventually gave way. It is a stark example of how climate change can indirectly set the stage for such dramatic events. The wave generated in Tarn Fjord was not just a localized surge, but an event with ripple effects that reached far beyond its Alaskan setting. Scientists have studied this incident extensively, using it to refine models and improve our understanding of how such waves propagate and amplify in confined environments. The research underscores the importance of considering local geography and geological history when assessing tsunami risk. Fjords like Taian are not unique in their susceptibility to such events. Across the globe, particularly in regions where glaciers are in retreat, similar conditions can be found. The steep, glacially carved walls of fjords make them inherently unstable, prone to rockfalls and landslides that, when they occur, can displace vast quantities of water in an instant. The amplification effect of the fjord's geometry can then transform this displacement into a towering wave. The potential for future events is closely tied to the ongoing shifts in our global climate. As temperatures rise, glaciers continue to melt, retreating further into the mountains and leaving once stabilizing ice-free slopes exposed to the elements. The risk of landslides increases, and with it, the likelihood of fjord megawaves. This interplay between climate change and geological processes is a poignant reminder of the interconnectedness of Earth's systems. Yet, it is not all foreboding. Scientists are actively working to monitor these environments, employing a range of technologies from satellite imagery to ground-based sensors. By keeping a close watch on glacial retreat and slope stability, they aim to better predict and perhaps even mitigate the impacts of future events. The lessons learned from Tarn Fjord and similar incidents around the world are invaluable in this endeavor. In reflecting on the power and beauty of fjords, one cannot help but marvel at their duality. They are places of serene beauty, drawing visitors to their shores with promises of tranquility and awe-inspiring vistas. Yet, beneath this calm exterior lies a latent energy, one that can be unleashed with staggering force under the right conditions. Understanding this balance is key to appreciating the full story of fjords and the waves they can harbor. As we continue to explore the natural world and its myriad wonders, the study of fjord megawaves offers both a cautionary tale and an opportunity for greater insight. In these deep, narrow inlets, we find a microcosm of the dynamic processes that shape our planet, a reminder of the Earth's ever-changing nature and the intricate dance between its many elements. In the quiet yet exacting world of geological science, the task of identifying ancient tsunamis is akin to piecing together a colossal, time-swept puzzle. Imagine, for a moment, a vast library where each book is a layer of sediment and each page a grain of sand, silt, or clay, meticulously placed by the hands of time. It is within these sedimentary archives that scientists strive to uncover the stories of past megawaves, revealing not just their occurrence, but their magnitude and reach. One of the foremost methods utilized in this detective work is sediment analysis. When a tsunami sweeps across the land, it does not merely wash over it, it leaves behind distinct deposits that differ markedly from other types of sedimentation. These deposits, known as tsunamiites, are often characterized by a chaotic mix of materials, marine shells, fragments of oceanic crust, and terrestrial debris, all mingled in a haphazard fashion. This turbulent cocktail is deposited over a short period, a stark contrast to the more orderly and stratified layers formed under normal conditions. To the trained eye, these layers can speak volumes. For instance, the presence of marine microfossils, such as foraminifera, found far inland within a sediment layer, suggest an oceanic origin, transported by a forceful surge of water. By carefully examining the composition and structure of these layers, scientists can begin to reconstruct the events that led to their formation. This is where the artistry of interpretation meets the rigor of analysis, as each layer must be understood within the complex tapestry of geological time. However, identifying the presence of a tsunami is only part of the story. Determining the age of these ancient events poses an entirely different challenge. To date these deposits accurately, scientists employ a variety of techniques, each with its own strengths and limitations. Radiocarbon dating is perhaps the most well-known method, particularly useful for organic materials such as plant remains or shell fragments trapped within the sediments. By measuring the decay of carbon isotopes, researchers can estimate the age of a sample with remarkable precision, though this method is limited to the past 50,000 years or so. For older deposits, other techniques come into play. Optically stimulated luminescence, OSL, dating, for example, measures the last time sediment grains were exposed to sunlight. When these grains are buried by a tsunami, they become shielded from light, effectively resetting the luminescence clock. By shining a light on these grains in the lab, scientists can release the stored energy and calculate the time elapsed since the last exposure. This method extends the reach of dating far beyond the confines of radiocarbon techniques, allowing insights into events from hundreds of thousands of years ago. Nonetheless, the interpretation of these findings is far from straightforward. The geological record is not an unblemished chronicle, it is a palimpsest, overwritten and obscured by subsequent natural processes. Erosion, bioturbation, and human activity can all conspire to confuse or erase the traces left by ancient tsunamis. Thus, scientists must tread carefully, corroborating evidence from multiple sites and employing an array of dating methods to build a robust understanding of past events. In addition to sedimentary evidence, geomorphological indicators also play a crucial role. Coastal landscapes bear the scars of tsunamis in their very contours. High-energy waves can carve out terraces, transport boulders, and reshape shorelines, leaving behind a geomorphic fingerprint. By studying these features, researchers can glean insights into the strength and direction of the waves, further piecing together the puzzle of past tsunamis. The identification of ancient tsunamis, therefore, rests on a delicate balance of evidence. It requires a synthesis of sedimentary clues, dating techniques, and geomorphic observations, all underpinned by an understanding of the regional geological history. It is a meticulous process, demanding both precision and patience as researchers strive to unlock the secrets held within the Earth's layers. Yet, despite the challenges, the rewards of this endeavor are profound. By unraveling the history of past tsunamis, scientists gain invaluable insights into the dynamics of our planet's oceans and coasts. These findings not only illuminate the past, but also inform our understanding of future risks, guiding efforts to mitigate the impact of potential mega-tsunamis. In this way, the study of ancient tsunamis serves as a poignant reminder of the interconnectedness of Earth's systems. It is a testament to the enduring power of natural forces and a call to deepen our understanding of the world around us. Through the lens of science, we are afforded a glimpse into the vast, intricate web of time, where each grain of sand, each layer of sediment, tells a story of the ever-changing dance between land and sea. In our quest to understand the formidable power of mega-tsunamis, numerical simulations have emerged as an invaluable tool. These simulations allow us to explore scenarios that are, thankfully, infrequent in our natural world. They offer a window into the processes and potential impacts of these colossal waves, helping us to prepare for events that may occur only once in many generations. As with any scientific tool, however, they come with their own strengths and limitations, each influencing the conclusions we may draw. At the heart of these simulations lies a blend of complex mathematics and computer technology. By creating models of the Earth's surface and the oceans, scientists can simulate how water might behave under certain conditions. These conditions might include an underwater landslide, a volcanic eruption, or even the impact of an asteroid. The power of these simulations is their ability to manage variables that would be impossible to experiment with in the real world, given the scales and energies involved. Numerical models rely heavily on what we call boundary conditions. These are the parameters set at the outset of a simulation, based on our best understanding of the physical situation. For instance, in modeling a landslide-generated tsunami, scientists must estimate the volume of the material displaced, the speed at which it moves, and the characteristics of the seabed. These initial conditions are critical, as they influence the simulation's outcomes. A small change in the input can lead to significantly different predictions, demonstrating the sensitivity of these models to their starting assumptions. One of the primary strengths of numerical simulations is their ability to enhance our understanding of wave propagation. By observing how a simulated tsunami might spread across the ocean, scientists can better predict how quickly and intensely waves might reach distant shorelines. This understanding is crucial for developing early warning systems and devising evacuation plans for coastal communities. Furthermore, simulations can be repeated under slightly altered conditions to explore a range of possible outcomes, providing a spectrum of scenarios rather than a single deterministic result. However, the limitations of numerical simulations should not be overlooked. Perhaps the most significant is the inherent uncertainty in initial conditions. Many of the parameters required to set up a simulation, such as the precise geometry of a landslide or the dynamics of a volcanic eruption, are not always well understood. This lack of precise data can lead to uncertainties in the simulation results. Moreover, while simulations can model the movement of water with impressive accuracy, they sometimes struggle to account for the complex interactions between water and the land it inundates, especially in areas with intricate topography. Another limitation is the computational power required. Simulating a mega-tsunami in detail demands significant resources. These simulations can be time-consuming and may require the use of supercomputers, especially when attempting to model large-scale events that affect vast areas. As technology advances, this barrier is gradually being lowered, but it remains a significant consideration. Despite these limitations, the role of numerical simulations in understanding mega-tsunamis cannot be underestimated. They allow us to explore hypothetical scenarios that are beyond the reach of direct observation. For example, by simulating a volcanic island collapse, scientists can assess potential wave heights and travel times, providing valuable information for risk assessment and mitigation strategies. In recent years, advances in technology and methodology have led to improvements in these models. Increased computational power, coupled with more sophisticated algorithms, has enhanced the accuracy and reliability of simulations. Additionally, the integration of real-world data, such as satellite observations and geological surveys, has helped refine these models further. This progress has not only improved our ability to model potential future events, but also allowed us to reconstruct past events with greater confidence. A noteworthy example of these advancements can be found in the modeling of the 1958 Lituya Bay event. By inputting detailed geological data into simulations, scientists have been able to recreate this historic mega-tsunami, offering insights into how such an event unfolded. These reconstructions not only enhance our understanding of historical events, but also validate the models themselves, providing a benchmark against which future simulations can be measured. In conclusion, while numerical simulations may have their limitations, they remain an indispensable tool in the study of mega-tsunamis. They provide a means to explore the potential impacts of these rare but powerful natural events, offering insights that are critical for preparedness and mitigation. As technology continues to advance, we can expect these simulations to become even more precise, helping us to better understand and anticipate the formidable forces of nature that shape our world. As we continue to refine these models, they will undoubtedly play a crucial role in our ongoing efforts to safeguard lives and livelihoods against the unpredictable power of the sea. As we find ourselves contemplating the vast and mysterious expanse of the ocean, it is natural to wonder about the immense forces at play beneath its surface. The concept of a mega-tsunami traversing the entirety of an ocean is both awe-inspiring and slightly unnerving. To unpick this idea, we must delve into the nature of these colossal waves, their origins, and the factors that influence their propagation across such vast distances. When a mega-tsunami is born, often from a sudden and dramatic geological event, it carries with it a tremendous amount of energy. This energy is initially concentrated and localized, much like the ripples formed when a stone is dropped into a pond. At its birth, the wave's energy is concentrated within a small area, resulting in immense wave heights, particularly near the source. This is where the term mega-tsunami truly earns its prefix, with waves potentially reaching hundreds of meters in height as they strike nearby coastlines. However, as this energy begins to traverse the ocean, it becomes subject to the inexorable laws of physics that govern wave dynamics. The energy of a wave is not infinite. As it propagates across the open ocean, it is both dispersed and diminished. This phenomenon can be likened to the spreading of light from a torch. intense near its source, but gradually dimming as it spreads further afield. This dissipation of energy is due to several factors. One of the key principles at play is the inverse square law, which implies that the energy of a wave diminishes in proportion to the square of the distance traveled. As the wave spreads outwards, its energy is distributed over an ever-increasing area, reducing the wave height and intensity. In addition, the ocean itself acts as a vast, energy-absorbing medium. The frictional interaction between the moving water and the ocean floor, as well as internal wave-breaking processes, contribute to the gradual loss of energy. Moreover, the immense depths of the ocean further influence wave behavior. In deep waters, the wave's energy is not confined to the surface, but extends downwards, diffusing through a greater volume of water. This vertical distribution of energy also contributes to the reduction in wave height as the wave travels. Thus, the once towering wave becomes a more modest swell as it moves across the ocean. The geometry of the ocean basin and the presence of underwater topography also play crucial roles. The seabed is not a uniform flat plain, it is a dynamic landscape of ridges, trenches, and plateaus. These features can reflect, refract, and scatter the wave energy, further diminishing its potency and altering its path. In some cases, underwater ridges can act as barriers, effectively shielding distant shores from the full force of a wave's impact. To illustrate this, let us consider a historical example from the annals of tsunami research. The 1958 Lituya Bay event, for instance, created a wave of extraordinary height due to its unique local geography. However, this wave did not cross oceans, it was confined within the bay. Similarly, when we examine submarine landslide events, such as the Storegga Slide off the coast of Norway, we find that while they triggered significant waves locally, their energy dissipated rapidly with distance, limiting their impact on faraway shores. While the notion of a wave traveling unimpeded across an entire ocean is captivating, real-world observations reveal that the energy of even the most potent mega-tsunamis tends to be curtailed by these natural processes. The Earth's oceans, expansive and formidable though they are, possess inherent characteristics that resist the unmitigated transmission of such massive energy over colossal distances. In our modern age, advanced modeling techniques allow scientists to simulate and predict the behavior of tsunamis with increasing precision. These models incorporate a variety of factors, including wave energy, ocean depth, seabed topography, and even the Coriolis effect, which arises from the Earth's rotation. By running these simulations, researchers can better understand the potential propagation of tsunamis and identify regions that may be at risk. One key insight from such studies is that while mega-tsunamis can certainly travel great distances, their ability to retain catastrophic wave heights over entire oceanic expanses is limited. The energy loss mechanisms we have explored ensure that by the time a mega-tsunami reaches distant shores, it is typically a shadow of its original self. However, it is essential to note that while the threat of a mega-tsunami crossing an entire ocean remains low, coastal communities must remain vigilant. The unpredictability of natural events and the complexity of ocean dynamics mean that continued monitoring and preparedness are vital. The implementation of robust early warning systems and public education can significantly mitigate the risks posed by tsunamis, regardless of their origin. Ultimately, the study of mega-tsunamis, like much of geoscience, is an exercise in understanding the balance between immense natural forces and the subtle resistances that modulate them. It is a reminder of the intricate tapestry of interactions that govern our planet, a complex dance of energy and matter that has shaped the Earth over eons. As we continue to explore these phenomena, we deepen our appreciation for the dynamic equilibrium that allows life to flourish amidst the ever-changing forces of nature. In the calm expanse of the world's oceans, a network of silent sentinels quietly performs its duty, an unseen guardian against the threat of tsunamis. These are the DART buoys, or Deep Ocean Assessment and Reporting of Tsunami Systems, each a marvel of modern engineering and a testament to our commitment to understanding and mitigating the forces of nature. These buoys, scattered strategically across the ocean's breadth, are part of a broader tapestry of monitoring and early warning systems designed to offer precious time and insight when the sea stirs with unusual intent. The DART system, developed in the late 20th century, represents a significant leap forward in tsunami detection. Each buoy is a complex instrument composed of surface and subsurface elements. Anchored to the ocean floor, a pressure sensor continuously measures changes in sea level, detecting the subtle shifts that may signal the passage of a tsunami wave. This information is relayed to the surface buoy, which in turn transmits data to monitoring stations via satellite. The process is not only about detection but also about communication, ensuring that the information reaches those who can interpret it and sound the alarm. The effectiveness of DART buoys lies in their ability to detect tsunamis generated by undersea earthquakes, which are responsible for the majority of such events. When the tectonic plates slip and the ocean floor is displaced, a signal is sent rippling through the water, and the vigilant buoys stand ready to capture it. However, the system has its limitations. It is less adept at identifying tsunamis caused by landslides, a mechanism fundamentally different from seismic activity. Landslide-generated tsunamis present a unique set of challenges. Unlike the tectonic shifts that often offer some degree of predictability, landslides can occur with little warning. They may be triggered by a sudden release of geological tension or by the collapse of volcanic island flanks, as we have explored in previous discussions. The rapid displacement of water by such mass movements can generate powerful waves, but these events may not produce the clear signals that seismic tsunamis do. The pressure changes are abrupt and localized, often evading the detection capabilities of systems spread across vast oceanic distances. In response to these limitations, scientists are continually refining the methods and technologies used in tsunami monitoring. Seismic sensors, for instance, are crucial in detecting the initial tremors that might precede a landslide. These sensors are part of a global network that records and analyzes the Earth's movements, offering clues that can help anticipate potential landslide sites. Yet, the unpredictable nature of landslides means that even with advanced monitoring, the warning times can be much shorter than for seismic tsunamis. In recent years, there has been a growing interest in the potential of GPS networks to enhance tsunami detection. These systems, traditionally used for navigation and location tracking, have shown promise in detecting the minute deformations of the Earth's crust that accompany significant seismic events. The integration of GPS data with existing monitoring systems could improve the accuracy and speed of tsunami warnings, particularly in coastal regions where time is of the essence. Despite these advancements, challenges remain. The vastness of the ocean and the complexity of geological processes mean that no single system can provide complete coverage or infallible predictions. Efforts are continually underway to expand the network of dart buoys and improve the sensitivity and reliability of seismic and GPS systems. Researchers are also exploring how machine learning and artificial intelligence might be harnessed to process the immense volumes of data generated by these networks, identifying patterns and anomalies with greater speed and precision than human analysts alone. The limitations in detecting landslide-based tsunamis highlight the importance of embracing a multifaceted approach to monitoring. Coastal communities, particularly those near known landslide-prone areas, must rely on a combination of technological innovation and local preparedness. Education and awareness campaigns play a crucial role in ensuring that residents understand the risks and know how to respond when warnings are issued. In reflecting on the capabilities and constraints of modern monitoring systems, we are reminded of the delicate balance between human ingenuity and the unpredictable forces of nature. Our technologies have brought us closer to understanding and anticipating the movements of the sea, yet they also underscore the inherent uncertainties that remain. It is a landscape of continual learning and adaptation, where each advancement builds upon the knowledge and experience of those who have come before. As we gaze toward the horizon, we do so with a blend of humility and hope. The systems we have developed are among the most sophisticated tools in our arsenal against natural disasters, yet they are part of a broader tapestry of resilience. It is a tapestry woven from threads of science, community, and an enduring commitment to safeguarding our shared world. Through this lens, the story of modern monitoring and early warning systems is one of both profound achievement and ongoing challenge, a narrative that invites us to remain ever curious and ever vigilant in our exploration of the Earth's dynamic rhythms. As we delve into the intricacies of our ever-changing climate, we find ourselves at the confluence of natural processes that stretch across vast temporal scales. The Earth's climate is, after all, a tapestry woven over millennia, each thread a delicate interplay of atmospheric, oceanic, and terrestrial forces. In recent decades, however, the pace of change has accelerated, driven by human activity, and with it comes an array of potential consequences, including the subtle yet significant risks of future tsunamis. At the heart of this discussion lies the notion of sea level rise. The relentless melting of polar ice caps and glaciers, coupled with the thermal expansion of seawater as it absorbs heat, contributes to a gradual but inexorable rise in global sea levels. This phenomenon, though measured in millimeters per year, accumulates over time, altering coastlines and rendering them more susceptible to the impact of waves. One might imagine this as a slow, quiet swell in a vast ocean, imperceptible at first, but transformative in its cumulative effects. When we consider tsunamis, particularly those of a mega-tsunami scale, the implications of rising sea levels become more pronounced. As sea levels rise, coastal areas, home to a significant portion of the human population, become increasingly vulnerable. the added water volume can exacerbate the reach and impact of any significant wave event, pushing seawater further inland and potentially affecting areas that might previously have been considered safe. Yet, the link between climate change and tsunamis is not solely a matter of sea levels. It is also intricately tied to the stability of the Earth's slopes and the behavior of glaciers, particularly in regions where these icy giants meet the ocean. Glaciers, those majestic rivers of ice, are not simply relics of the last ice age. They are dynamic entities, constantly shifting and reshaping the landscapes they inhabit. As global temperatures rise, the rate of ice melt increases, and with it, the potential for instability. In regions such as Greenland and Alaska, where glaciers terminate in the ocean, the accelerated melting increases the likelihood of calving events, where chunks of ice break off and plunge into the sea. These events, while often localized, can displace significant volumes of water, generating waves that may resonate through narrow fjords, amplifying their height and energy. In this sense, climate change acts as a catalyst, heightening the frequency and potentially the magnitude of such events. Furthermore, the warming climate can destabilize underwater slopes, particularly those laden with gas hydrates, methane trapped within a lattice of water ice found beneath continental shelves. As ocean temperatures rise, these hydrates can become unstable, leading to sediment slumps and submarine landslides. Such movements, though hidden from view, have the capacity to generate waves of considerable power, depending on their scale and speed. The potential risks are not confined to the polar regions or the deep ocean. Volcanic islands, with their steep and sometimes fragile flanks, are also susceptible to the effects of a warming world. As sea levels rise, the added pressure of water can exacerbate existing weaknesses in the rock, contributing to the risk of landslides and flank collapses. Here, the marriage of geological and climatic processes presents a unique challenge, requiring close monitoring and a nuanced understanding of the local environment. While these scenarios paint a picture of potential hazards, it is important to approach the subject with measured consideration. The Earth is vast and resilient, and while climate change may increase the frequency or magnitude of certain events, the probability of a mega-tsunami impacting human populations remains low. However, this does not diminish the importance of preparedness and continued scientific inquiry. The science of climate and tsunamis is complex, grounded in observation, modeling, and an ever-growing body of knowledge. As researchers employ advanced techniques to study the interactions between atmospheric conditions, oceanic behavior, and geological processes, our understanding will continue to evolve. This knowledge, in turn, informs the development of early warning systems and risk assessments, crucial tools in mitigating the impact of natural disasters. In reflecting upon the future, we are reminded of the delicate balance that characterizes our planet, a balance that is both a marvel and a responsibility. As stewards of this Earth, it is incumbent upon us to heed the lessons of the past, to harness the insights of science, and to act with foresight and humility. For in understanding the connections between climate change and tsunami risk, we are not merely anticipating potential disasters, we are engaging in the broader endeavor of safeguarding our shared home, ensuring that future generations may inherit a world as rich and vibrant as the one we now inhabit. In the quiet recesses of our planet's geological memory, the specter of mega-tsunamis looms with both intrigue and potential peril. As we turn our gaze towards the future, the question that naturally arises is whether these colossal waves could indeed visit our shores once more. To explore this, we must first examine the mechanisms and conditions that render such events plausible. One of the most credible scenarios for future mega-tsunamis involves volcanic island flank collapses. These islands, with their towering volcanoes, are often structurally unstable due to the accumulation of volcanic material over millennia, combined with the forces of erosion and gravitational pull. This precarious balance can sometimes tip, resulting in massive sections of the island breaking free and plunging into the ocean. Such collapses have occurred in the past, notably in Hawaii and the Canary Islands, sending waves of unimaginable scale across ocean basins. While significant research suggests that these events are relatively infrequent, the potential energy they unleash upon failure demands our attention. Another prime candidate for future mega-tsunamis lies in the realm of submarine slope failures. The ocean floor, particularly along continental margins, is a dynamic and evolving landscape. Here, sediment accumulation, compounded by the presence of gas hydrates and the occasional seismic jolt, can lead to large-scale slope instability. Recent advances in ocean floor mapping have revealed past failures, painting a picture of an ever-shifting underwater world. Some of these events, such as the Storegga Slide off the coast of Norway, have had profound impacts on coastal regions far and wide. While our understanding of these processes is growing, predicting their occurrence remains a complex challenge. In the icy realms of fjords and glacial regions, we find another potential source of mega-tsunamis. As glaciers retreat and destabilize, the potential for massive calving events increases. When large chunks of ice break away from glaciers, they can displace significant volumes of water, generating waves that travel far beyond their point of origin. Recent events in Alaska's Tarn Fjord underscore the power and unpredictability of these glacial interactions. With climate change accelerating the melting of ice and the retreat of glaciers, the likelihood of such events may be on the rise, posing newfound risks to nearby communities. Asteroid impacts, while extremely rare on human timescales, represent the final scenario where mega-tsunamis could occur. The collision of a large celestial body with Earth's oceans would create waves of unprecedented magnitude. The Chicxulub impact, which is believed to have contributed to the extinction of the dinosaurs, serves as a stark reminder of the power these events can unleash. However, given their rarity, these impacts are more a subject of scientific curiosity than immediate concern. Geographical hotspots for potential future mega-tsunamis tend to coincide with regions of known geological instability. The Pacific Rim, often referred to as the Ring of Fire, is home to numerous active volcanoes and tectonic plate boundaries, making it a region of heightened interest. Similarly, the North Atlantic, with its history of submarine slides and volcanic islands, remains a focal point for researchers. The growing body of scientific literature underscores the importance of continued monitoring and study. Modern technology, including satellite observation and advanced underwater sensors, offers new ways to detect early signs of instability. These tools, combined with numerical modeling, enhance our ability to predict and prepare for potential mega-tsunamis. Yet, despite these advancements, there remains an element of unpredictability inherent in Earth's natural processes. While mega-tsunamis are rare, their potential impact on coastal communities worldwide cannot be ignored. As populations continue to grow and urbanize along coastlines, the need for comprehensive risk assessments and preparedness plans becomes ever more pressing. Understanding the signs, improving early warning systems, and fostering collaboration among nations are critical steps in mitigating the risks associated with these formidable natural events. In contemplating the possibility of future mega-tsunamis, we are reminded of the delicate balance between human civilization and the forces of nature. The Earth, in its dynamic splendor, continues to evolve, shaping and reshaping its landscapes in ways that can sometimes defy our understanding. Yet it is through this exploration of the unknown that we gain insight not only into the planet's past, but also its potential future. As we reflect on these scenarios, the importance of curiosity and preparedness becomes apparent. By studying the past and investing in scientific research, we strive to coexist with the natural world, respecting its power and unpredictability while safeguarding our own existence. In this endeavor, we find not just the possibility of understanding, but the promise of resilience. As we draw our exploration to a contemplative close, we are reminded of the profound lessons that our planet's history has to offer. In the quiet pages of geological time, the Earth has recorded events of unimaginable scale. Among them, the colossal waves we have come to know as mega-tsunamis. These natural phenomena, though rare, serve as a testament to the dynamic processes that shape our world. They are not merely relics of the past, but are whispers of the Earth's potential to surprise and challenge us anew. The study of mega-tsunamis is akin to reading an ancient, weathered manuscript, with each chapter revealing the interplay of forces that govern our planet's behavior. Through the diligent work of scientists, we have begun to decipher these narratives, piecing together the fragments of evidence left by waves that once roamed across vast expanses. Each discovery adds depth to our understanding, illuminating the conditions that give rise to such events and the likelihood of their recurrence. Geological history, in its vastness, offers a lens through which we can appreciate the resilience and fragility of our world. It teaches us that while mega-tsunamis are exceptionally rare, they are part of the planet's natural processes, driven by mechanisms that are, themselves, a testament to the Earth's inherent dynamism. From the immense energy of volcanic eruptions to the silent shifts of submarine slopes, these events echo a powerful reminder of the forces that lie beneath the surface, often unnoticed until they manifest in dramatic displays. In interpreting these past events, scientists have developed sophisticated models and methods, crafting simulations that attempt to capture the complexity of Earth's systems. These models serve as both tools of understanding and instruments of prediction, allowing researchers to explore scenarios that might unfold in the future. Yet, the task is not without its challenges. The inherent uncertainties in modeling such rare phenomena require a careful balance of assumptions, each influencing the outcome of the predictions. As our comprehension deepens, so too does the precision of these models, offering a clearer picture of what might be expected and how we might best prepare. The ongoing research into mega-tsunamis is more than an academic pursuit. It is a crucial endeavor for the safety and well-being of communities around the globe. The insights gleaned from past events inform modern hazard science, guiding the development of early warning systems and risk assessments. By understanding the conditions under which mega-tsunamis occur, we can better predict their likelihood and mitigate their impacts, enhancing resilience in regions that may be vulnerable to such rare but potentially devastating events. As we look to the future, the importance of continued research cannot be overstated. The Earth's systems are intricate and interconnected, influenced by factors both terrestrial and celestial. With a changing climate and shifting tectonic plates, the landscapes we inhabit are in a state of constant evolution. It is within this context that the role of scientific inquiry becomes vital, providing the knowledge and tools necessary to navigate an uncertain future. In reflecting on our journey through the world of mega-tsunamis, we are reminded of the delicate balance that sustains life on Earth. It is a balance shaped by forces that are both ancient and ever-present, capable of great creation and, occasionally, of great upheaval. The story of mega-tsunamis, then, is not simply one of destruction, but of the intricate dance of elements that define our planet. As we continue to study these phenomena, we do so with a sense of humility and wonder, acknowledging the vastness of what we have yet to understand. The pursuit of knowledge is a journey without end, one that invites us to look beyond the horizon and to ponder the mysteries that lie just out of reach. In doing so, we are not only better equipped to face the challenges of tomorrow, but are also enriched by the beauty and complexity of the world we call home. In this narrative of Earth's past, we find a quiet assurance that through understanding, we gain the ability to anticipate and adapt, crafting a future that honors the lessons of history while embracing the possibilities of what is yet to come. It is a future where curiosity leads the way, where science serves as both guide and guardian, and where the wonders of our world continue to inspire.